All right, hi. I'm going to give you a short talk about PMTs, which is the short name for a photomultiplier tube. And trying to give an example of something that's a 10-minute talk about something like sensors. So let me start with what it is. So a PMT, or a photomultiplier tube, is essentially a very sensitive light detector. They come in all shapes and sizes, and they're used in a wide variety of applications, some of which I'll talk about at the end if I have time. But they've got, the common characteristics of these is that they have they're very, very sensitive. They can detect single photons. They can detect very small luminosities of light with a fair degree of linearity, and they can detect very, very short pulses of light. So these are used in lots and lots of applications. And although they are a very old technology, predating solid state devices, they remain in use today as being the standard for measuring small quantities of light, which is one of the things we do in particle physics experiments. Phototubes are relatively expensive, though. Their downside is they range from a few hundred to a few $1,000s, depending on how big they are, because they're very difficult to make, and only a few companies know how to do this very well. So let me walk you through one particular phototube here. They all have very similar characteristics. So on the top here, you can see that I have a PMT, and on the right-hand side, there is a photocathode, which is a piece of glass where the light is going to come in. In the middle, inside the tube, and this tube is made of glass and has all the air evacuated out, there is what we call the dynode chain, which is a series of pieces of metal. And then at the back, there's pins that connect to all these pieces of metal. And attached to the back is usually you have a base, which is a device that usually is used for regulating the voltages that go in, which I'll explain in a moment. So how this thing works. On the right-hand side, you have light coming in, and it goes through the glass because glass is transparent. And on the inside of the glass, you can see here, there's a thin film of metal. And the film is thin enough that you can, it's only semi-transparent. So that metal can absorb light. And when it absorbs light, so if it absorbs a photon here, there's, of course, the thing we know about from modern physics called the photoelectric effect. And that is that when a photon hits a metal, it can eject an electron. Now, the other thing we know is that the kinetic energy of this electron is going to be no bigger than the kinetic energy of this, the energy of the photon. And the energy of the photon is a few electron volts for visible light, 2 to 3 electron volts. So this thing has only got a few electron volts of energy. It's not very much energy. So how are we ever going to detect so we want to detect a single photon, we have to detect a single electron, but that's very, very difficult because this is a small amount of charge. So what we're going to do is we're going to amplify this, and this is where the multiplication comes in. So what we do is, instead of just collecting this electron, we instead show it a dynode here. So a dynode, this is the first dynode in the chain behind. And this dynode is a piece of metal that's shaped in some funny way. And what we do is we put this dynode at 100 volts above ground. And we put the photocathode at ground. There's other ways of doing this, but this is, one of the default ways in which people operate a phototube. So this electron, in this space, however big the space is, which can be quite small, this can be millimeters or centimeters, this electron will start accelerating towards this dynode plate and have 100 electron volts of energy when it gets there. Now, when you have a 100 electron volt of energy electron hitting that piece of metal, you have something that works just like the photoelectric effect, and that is that electron can impart its kinetic energy onto multiple other electrons in that lattice. So the crystal gives off like 3 or 4 electrons. Now these electrons, again, they have to escape the metal, and so they have to overcome the work function of the metal. And it's a very inefficient energy transfer process. So really, for one incoming electron, you might get 3, 4, 5 outgoing electrons. And there's some statistical variation on how many will come out on each occasion. But now we've got 3 electrons. Now the game we play is we just do it again. So here's the same picture left to right. So here's the light coming in, the electron comes through, hits the first dynode, hits the second dynode, hits the first dynode, gets a multiplication factor, hits the second dynode. Each one of those secondary electrons creates 4 more. Another dynode, each of those creates 4 more, and so on and so on and so on. So at every stage of this, you're increasing the number of electrons by about a factor of 4. And so if you have 12 of these, each one being 100 volts higher than the other one, so this is at ground, this is at 100 volts, 200, 300, 400, 500, 600, so you get 1200 volts at the end of this. That means you've multiplied your number of electrons by 4 times 4 times 4 times 4, 4 to the 12th. And 4 to the 12th is somewhere in the range of a million. 3 to the 12, 3.2 to the 12 is 10 to the 6. So you have a factor of about a million. About a million electrons is about 10 to the minus 13 coulombs. Now that's not a lot of charge still, but this all happens quite quickly because a single photon hitting it is not going to take very long. Now, not all the electrons follow the same paths, and so there's a spread of when the electrons arrive, but typically this is about 5 nanoseconds long. So if you work this out, this much charge in this much time, that gives you a current about 40 microamps, which isn't a lot, but it's enough. If you put that into, say, a 1 kilo ohm load, that's a 40 millivolt signal, and you can detect this on an oscilloscope, say. So here are some oscilloscope traces of single photons hitting a PMT, and the size of this pulse will be roughly the same for every time you get a single photon hit. If you get 2 photon hits, then this pulse will be about twice as big. You'll have twice as many original electrons, so you'll have twice as much charge. So this allows you to detect very, very small signals. One single photons can thus be multiplied up into these relatively large signals, which then you can read out without a lot of fancy electronics. You can take this signal and you can put it, for instance, through an op amp, a simple amplifier, and then digitize it in some way. There's lots of different ways in which this thing works. One of the real problems is you want to have as many electrons out the back as you can. And there's 2 parts to this. The first is the collection efficiency, how many of those electrons you actually manage to capture. In the first collision with the window. So the collection efficiency is if you make a photoelectron, do you manage to catch it on the first dynode? And that's usually somewhere like 80%, 90%. The real problem is the quantum efficiency, and that is what's the probability that if a photon hits the tube, it converts into an electron. If you make the metal too thick, the electron can't get out. If you make the metal too thin, then not enough of the photons hit the metal. And so this is this delicate game you have to play in creating the tube. So for well-created tubes, depending on the material you're using for the photocathode and depending on the glass and stuff like this, you might have different response curves. And you can see that these guys are sort of around the 30% level under normal conditions. There are ways of getting this much higher, but they require very special conditions like cryogenic materials and stuff like that. So this means that you have a 1 in 3 chance of detecting any given photon. You're still at single photon detection, but only a fraction of your photons do get detected. Now, how do you get these dinodes each to be 100 volts apart? Well, what we do is we feed in a single sort of 1 kilovolt, 1.2 kilovolt supply voltage. Then you take that and you put that on the anode, the very last one, the one you're reading out from. This is where the signal is going to be extracted. So you put 1,000 volts here and you put 0 volts on the cathode, and then you put resistors in between. And these are all equal resistors, and this thing makes a voltage ladder, which is something we've seen before. So this will be at 0 volts, 100 volts, 200 volts, and so on. So that's all easy. This capacitor right here is there because as often we have capacitors in the last few dinodes. And the reason is because when that last dynode or the anode loses that charge, that actually changes its voltage appreciably during that short moment of time. So by having a capacitor there, it gives you a reservoir so that it can recharge really, really quickly. Now, the problem is, of course, that this readout that we want is sitting on 1200 volts. So you'd see 1200 volts plus or minus 40 millivolts. Well, that's a problem because, you don't want to have 1200 volts going into your very sensitive amplifier detector. But again, that's a very trivial thing. All you need to do is put that through a blocking capacitor. That removes the DC offset, and so now you see only the AC current, and so this works completely well for taking off that high voltage offset. Phototubes, the phototube application, of course, that I'm most concerned with is the neutrino detectors, and this is a picture of Super Kamiokande. Each one of those tubes is, I believe, 20 inches across, so like 2 feet across. And there are something like 10,000 phototubes in Super Kamiokande. This is the experiment I worked on as a graduate student called the Sudbury Neutrino Observatory, which has, again, about 10,000 phototubes, each of which are about 6 inches, and this is looking into a sphere of them from the bottom. But they're used in a lot of other places: spectrophotometers, flow cytometers, anything that uses light to detect stuff, generally speaking, will use a PMT if it needs to be a sensitive device that works either with very small quantities of light or otherwise. So those are the basic ideas behind a photomultiplier tube. And this is the point where I would be asking for questions, which of course we can't do because this is a video. So I have been told at times not to thank your audience for their attention, but it's an easy thing to say to sort of make it clear that you're closing up the talk. It's good to have the first few words and the last few words completely memorized in your talk. The first few are more important. The last few are also nice, so you have a clear ending. Now, let me just go over a couple of points about giving a talk. And this is in the realm of art instead of science. You can violate any one of these rules, except the first one. These are rules that I have found are very helpful, especially for people who are starting out giving talks. And it's okay to abandon some of them some of the time. In fact, you probably saw me abandon some of them just now. So the first one is, of course, know your stuff. Don't just know what you're going to say. Understand the topic in some depth, because you're going to get questions. And if you don't understand it well, it's going to show. So you're going to want slides. Slides for scientific talks. For scientific talks is standard. Everyone expects to have something to look at. When you're arranging the number of talks, about 1 slide per minute is a good rule of thumb. So you should take about 1 minute to describe what's on a slide, and the slide should reflect what you are describing. Slides, you'll notice that my slides were all white. They don't have to be white, but you don't want a background that's very distracting. I prefer black on white. There are other things, it depends on what projector you're using or on a computer screen, but basically they shouldn't be busy. Don't have very busy or complicated backgrounds. When you have text on a slide, it's dangerous. Text is okay. You need text sometimes. You want to remind yourself of a few key facts. You want to communicate to the audience some things very clearly. The problem is with too much text, and the audience will read text instead of listening to you. Now, sometimes that's okay. If it's just a small amount, that's okay. But that's what you want. But you do not want to be reading the text at them. If you're reading the text at them, you're doing it wrong. If you were doing that, you might as well just give them the slides and let them do it themselves. If you find yourself reading verbatim, that's not what you should be doing. You should be doing all things extemporaneously. This is extemporaneous speaking, which is to say it's practiced. You know what you're going to say. You know crudely the order in which you're going to do it, but you're making it up as you go along at the moment. That's the best way of giving talks. It's the way we teach. It's spontaneous. You're reacting to your audience. You're not necessarily saying the same things every time. Sometimes you say it better and sometimes you say it worse. But a very rehearsed speech comes across to me as very stilted. Slides should have only things you want to talk about. Never put something on a slide that you don't want to talk about, because someone will raise their hand at the end and say, go back to slide 4. I didn't understand what this picture was showing me. Or I didn't understand what you meant by this thing. Don't put it on there unless you're willing to talk about it. They should never have something you don't understand. Never have something you don't want to talk about. It's okay to have something on a slide and you say, I don't have enough time to go into this. And in fact, that's actually a high-level technique, is to seed questions, to leave unanswered obvious questions that you want to answer, but you don't have enough time to answer. And then your audience someone in the audience may dutifully ask that question, and you say, I have a backup slide just for that thing. And you move to slide 12 or slide 13, and you have a complete answer that you can spend in about a minute on. It's a way of padding your talks out without using up more time. As I said earlier, memorize the first few things you're going to say. Have the first couple of sentences be completely scripted. It's okay if you go off script, but if you have that script, you can get into the role. It's the very hardest thing is getting started. So know what you're going to say right away. Know what your first few words are. Know what the first sentence is going to be coming out of your mouth. The title screen is actually really hard. And so you might want to have something you're going to say to introduce things really straight on. And not just, I am going to talk about blah. You it's best if you preface it. It's like, I really want to talk about PMTs because I use them all the time. I really wanted to talk about capacitive touchscreens because I've always been fascinated how my phone works. Right? Come up with a personal reason to get started. That'll make it really easier. The most important rule for giving any talk is practice. I can give a talk now with very minimal practice, but I've given this talk you just seen. I have done it in teaching. I have done it in electronics. I have given this talk probably 50 times in my life, maybe 100. I still practiced once. I ran through it in my head and knew what to do. Now, if you're not that practiced, you want to practice this multiple times. Practice it by yourself. Say the words out loud. That's, talk to your teddy bear, talk to a toy, talk to the wall. Talk out loud. It goes differently when you're talking out loud than when you're mumbling to yourself. You can record yourself. This is, of course, one of the nice things about this online regime is we're all getting used to this now. After you have practiced, go back and edit. You will start realizing that the things you're saying out loud are slightly confused, or you've forgotten what you're going to say next, and then you can go back and change your slides to revise that. Once you kind of got it in shape, practice it for someone else. Practice for your boyfriend, your girlfriend, your roommate, right? And these days, it's probably your parents because of the COVID scare. And then do it again, right? Now, don't over practice. You don't want to have every word memorized, like I said, but you do want to have practiced multiple times so you don't feel uncomfortable starting it. And this holds even if you're a comfortable speaker. You should go through this exercise more than once. The last rule is when you practice at least once, and maybe not the last one, is you should practice in the room you're going to give the talk. And in the case of this year's talks, that means you should open up a Zoom session, like a private Zoom session, and practice in front of it. Record it. Well, okay, maybe not record it. I can't stand to watch myself speak, but it's very, very helpful to use the tools you're going to use when you do it for real. Make certain that it looks good on the screen, right? So when you record the Zoom talk, and actually one thing I've done is I've attached a Zoom with my computer and then with my phone at the same time, and then looked and see what it looks like on my phone when I'm using the computer. Do it using the tools you're going to use for real, and then you won't get caught up in stupid technical details. In real life, what can often happen is the projector won't show the colors that you thought it could. So a picture or a diagram that looks excellent on your computer screen will look terrible and be completely impossible to read in a real world screen. And it's kind of hard to know what that's going to be true or not. I still get caught up by this stuff, and it depends on the projector, it depends on the room. So always, if you can, practice in the room or as close as you can get to that room when you're doing it. And there's also a lot of psychology that if you practice the same way you're going to do the real thing, you'll be better at it, you'll remember more of it. And so you should sort of try to do dress rehearsals every time. Wear the clothes you are going to wear, that kind of thing, especially if you're very nervous about talks. Now, I don't want to lay too much on you. This is only a 10-minute talk, but this is the idea. I want to give you some general rules for doing talks, and this is one of the opportunities we have for doing it. Okay, so I'm going to go back to my weekend. Everybody stay safe, and I will see you soon.